हेलो दोस्तों, आई होप आप सभी अच्छे होंगे। आपने हमारी पुरानी वीडियो देखी होगी, आपको कैसी लगी हमें कमेंट बॉक्स में बताते रहिएगा। और आज हम चलिए शुरू करते हैं आज की अपनी नई वीडियो।
A small pebble dropped in a pool of still water creates ripples on the surface. These ripples form concentric circular rings around the source of disturbance and spread outward along the surface. When these ripples reach a point on the surface of water, the point starts oscillating up and down. Different points, which are at the same distance from the source of the disturbance, oscillate in phase. That means all these points reach the crest or trough at the same time. The locus of all such points having the same phase of oscillation is called a wave front. In case of water waves on the surface of water, we observe circular wave fronts. Each circular wave front is a locus of all points having the same phase of oscillation. The propagation of the waves can be understood by studying the propagation of wave fronts. An outward normal drawn at any point on the wave front represents the direction of the wave at that point. In terms of energy, we say that the energy of the wave propagates in a direction perpendicular to the wave front. The speed at which a wave front travels is the speed of the wave. Waves on the surface of water are two-dimensional, and hence the wave fronts are circular in shape. But the waves from a source of sound or a source of light in a homogeneous medium spread in all directions and are three-dimensional in nature. Now consider a point source of light placed in a homogeneous and isotropic medium, emitting light waves in different directions. If the medium is homogeneous, the speed of light waves is the same throughout the medium, and if it is isotropic, it is the same in all directions. The loci of all points, which have the same amplitude and vibrate in the same phase, forms a sphere with its center at the source of light. Hence, a spherical wave front is generated when a point light source is placed in a homogeneous medium. At a large distance from the source, these spherical wave fronts have large radii of curvatures. A small portion of a spherical wave front at a very large distance from the source can be treated as a plane wavefront. In physical optics, we visualize light as waves and wave fronts. In ray optics, we visualize light as rays. A line drawn perpendicular to the wave front in the direction of its propagation is treated as the ray of light in ray optics. Note that a wave front is a surface of constant phase. If a particular wave front is a locus of points with maximum amplitude, it continues to be like that as it propagates through the medium. Christian Huygens proposed a geometrical method known as the Huygens principle for finding the shape and location of a wave front at some instant from the knowledge of the shape and location of the same wave front at an earlier instance. According to Huygens' principle, each point of a wave front is a source of a secondary disturbance and generates spherical secondary wavelets, which spread out in all directions with the speed of the wave in that medium. If a tangential surface common to all these secondary spherical wavefronts is drawn, then it gives the new position of the wavefront at a later instant. This surface envelopes all the secondary wavelets. To understand Huygens' principle, Let us now consider a primary wave front AB propagating in a homogeneous medium. Then, according to the Huygens principle, each point of AB acts as a source of secondary disturbance. The secondary wavelets emanated from these points are spherical in shape and spread in all directions at a speed equal to the speed of the wave. If the speed of the wave is v, then in time t, the radius of the spherical wavelets becomes vt. The tangential surface common to all these spheres in the forward direction gives the shape and location of the new wavefront after t seconds. In the image, the surface A'(B' represents the location of the wavefront AB after t seconds. The secondary wavelets must be directed backward as well as forward from the secondary point sources. If this would be correct, we would get a surface such as A'(B') as a back wave. But experimental results do not show the presence of any such back wave. In order to explain this, Huygens proposed that the intensity of the spherical wavelets is not uniform in all directions, but is maximum in the forward direction and zero in the backward direction. Hence, the wavelets as well as the whole wave always propagate in the forward direction only. Now let us use Huygens' principle to find the location and shape of a plane wavefront at a later instant of time t. Let AB be a plane wavefront at time t equal to 0. According to Huygens' principle, each point of AB acts as a source of secondary wavelets. The radii of these spheres will be Vt after t seconds. The plane touching these small spheres in the forward direction gives the shape and location of the new wavefront after t seconds. When light waves are incident on an interface of two transparent media, light gets partially refracted and partially reflected. Using the Huygens principle, we can derive the laws of refraction and reflection and show that these laws are consistent with the wave nature of light. Let us first consider the refraction of light when it propagates from a rarer medium to a denser medium. Let SS' be the boundary of the two transparent media, medium 1 and medium 2, in which the speeds of light are v1 and v2 respectively. Consider a plane wavefront AB in medium 1 that is propagating towards the interface SS'. A normal to the wavefront in the direction of its propagation gives the direction of the wave. Let A'(A) be the direction of the wavefront AB in medium 1. If I is the angle between the wavefront AB in medium 1 and the interface SS', then the angle of incidence is also equal to I. Assume that at t is equal to 0, only point A of the wavefront AB is in contact with the interface SS'. The shape and the location of the wavefront at any subsequent instant of time can be found by constructing secondary wavelets. Since point A is on the interface SS', part of the secondary wavelet originated from this point refracts into medium 2 and a part is reflected back into medium 1. If reflection at the interface is neglected, hemispherical wavefronts from point A propagate into medium 2. As the wavefront travels from medium 1 to medium 2, different points of the wavefront are incident on the interface SS- at different instants of time. If the point B is incident on the interface at C after t seconds, then BC is equal to V1t. Since the speed of the light in medium 2 is V2, during the same period, the secondary wavelet generated at point A at time t is equal to 0, will have formed a hemisphere of radius V2t. Secondary wavelets from different points on the interface form hemispheres of different radii in medium 2. If we construct a plane CD tangential to all these hemispherical secondary wavelets, it would represent the refracted wave front after t seconds. Note that AD, being the radius of the hemispherical wavelet generated at A, it is equal to V2t, and the direction of AD is the direction of the refracted wave in medium 2. If the angle made by the refracted wave front CD with the interface SS- is R, then it is same as the angle of refraction. Since angle BAC is equal to I, from the triangle ABC we have sin I is equal to BC by AC. Similarly, as the angle ACD is equal to R, from the triangle ACD we have sin R is equal to AD by AC. From these two equations, we get sin I by sin R is equal to BC by AD. On substituting the values of BC and AD in the equation, and on further simplification, we get sin I by sin R is equal to V1 by V2. Let this be equation 1. We know that if light travels from a rarer medium to a denser medium, it bends towards the normal, and hence the angle of refraction, R, is less than the angle of incidence, I. From equation 1, we can conclude that if R is less than I, then V2 must be less than V1. Thus, according to Huygens wave theory, the speed of light in a denser medium is lesser than the speed of light in a rarer medium. This is in contradiction to the assumptions made by Newton in his corpuscular theory of light. In 1850, it was Foucault who first determined the speed of light experimentally and confirmed that the speed of light indeed is less in water than in air. If c is the speed of light in vacuum, then the refractive index of medium 1, N1, is equal to c by V1, and the refractive index of medium 2, N2, is equal to c by V2. Therefore, N1 by N2 is equal to V2 by V1, which can also be written as V1 by V2 is equal to N2 by N1. Let this be equation 2. From equations 1 and 2, we can write sin I by sin R is equal to N2 by N1. This can also be written as N1 sin I is equal to N2 sin R. This is Snell's law of refraction. Let us now consider the refraction of successive wave fronts at the interface SS-. If the wave fronts as shown represent crests of a wave, then the distance between the two successive wave fronts in a medium is equal to the wavelength of light in the medium. Let the wavelength of light in medium 1 be lambda 1, and in medium 2 be lambda 2. If the wavefront AB is considered, the points A and B reach the points D and C at the same time. As such, the number of wavefronts between B and C is equal to the number of wavefronts between A and D. Therefore, BC by AD is equal to lambda 1 by lambda 2. Since BC is equal to V1T and AD is equal to V2T, we have lambda 1 by lambda 2 is equal to V1 by V2. Let this be equation 3. Equation 3 implies that when a light wave refracts into a denser medium, its wavelength as well as velocity decreases. From equations 1 and 3, we can write sin I by sin R is equal to lambda 1 by lambda 2. In case of light traveling from a denser medium to a rarer medium, the refraction of light is as shown. Using Huygens principle, we can prove equation 1 for refraction of light when it travels from a denser to a rarer medium. Since the speed of light in medium 1 is less than the speed of light in medium 2, the angle of incidence is also less than the angle of refraction. If the angle of incidence I is increased, correspondingly, the angle of refraction also increases. For a particular angle of incidence known as critical angle, the angle of refraction becomes 90 degrees and the wave grazes along the interface SS'. If the angle of incidence is greater than the critical angle, we will have total internal reflection. As such, the laws of refraction are consistent with the wave nature of light. In ray optics, you have already studied about the laws of reflection. Now, we shall study them again, but with wave theory as the basis. In order to prove the laws of reflection based on wave theory, let us consider the reflection of a plane wavefront A', B' from a plane reflecting surface SS'. Let AB be the position of the wavefront when it just touches the reflecting surface at the instance t is equal to 0. A' gives the direction of propagation of the wavefront, and let us assume that the wavefront is incident on the surface SS' at an angle I, and the speed of the light in the given medium is v. At t is equal to 0, the point A is in contact with the surface SS'. The secondary wavelets from points other than A have maximum intensity in the forward direction and zero intensity in the backward direction, and thus they travel in the forward direction. Since the surface SS' is a reflecting surface, the intensity of the secondary wavelets from A is maximum in the backward direction and minimum in the forward direction. Thus, we can say that the secondary wavelets from A propagate back into the same medium. Let us assume that after t seconds, the point B of the wavefront AB is incident on the surface SS' at point C. Then, BC is equal to VT. During the same period, the hemispherical secondary wavelet from A would also have attained a radius equal to VT. Hence, a hemisphere with its center at A and radius equal to VT represents the secondary wavelet that originated from A at time t is equal to 0. If a surface, such as CE, tangential to the hemispherical wavefront and passing through the point C, is constructed, then CE would represent the reflected wavefront. AE is the radius of the hemispherical wavelet generated at the point A and is equal to Vt. That means AE is equal to BC is equal to Vt. The angle that the reflected wavefront CE makes with the surface SS' is the angle of reflection. Let it be theta. The two triangles AEC and ABC are right-angled triangles with a common side AC and with two other equal sides AE and BC. Therefore, these two triangles are congruent. Hence, the angle BAC is equal to the angle ACA. This means the angle of incidence I is equal to the angle of reflection theta. This is the law of reflection. Let us now understand the behavior of a plane wavefront as it undergoes refraction through a prism as well as through a lens. Consider a plane wavefront AB passing through a glass prism. As the wavefront AB passes through the prism, the point A travels for longer distances in the glass than the point B. Since the speed of light waves is less in glass, point A and the lower portion of the wavefront passing through the prism are delayed, and as a result, there is a tilt in the emerging wavefront A'-B'. When a plane wavefront is refracted through a convex lens, it becomes a converging spherical wavefront and converges at a point on the principal focus. On the other hand, if a plane wavefront is refracted through a concave lens, we get a diverging spherical wavefront. If a plane wave is incident on a concave mirror, upon reflection, it becomes a converging spherical wave. Note that the time taken from a point on the object to the corresponding point on the image is the same measured along any ray. Observe the image formation of a point object placed before a convex lens. Although the ray going through the center traverses a shorter path, because of the slower speed in glass, the time taken is same for rays traveling near the edge of the lens. Let us now discuss about the Doppler effect of light. The apparent change in the frequency of light due to the relative motion between the source of light and the observer is called the Doppler effect. You have already studied about the Doppler effect related to sound waves. Let us recollect the expressions we had derived for the Doppler effect of sound waves. Let Vs be the velocity of the source, Vo be the velocity of the observer. Both these velocities are relative to the medium in which they propagate and act along the line joining them. Also, let nu0 be the frequency of sound when the source and the observer are stationary. Nu be the frequency when the source is in motion and the observer is at rest. And nu' be the frequency when the observer is in motion and the source is at rest. Then, as for the Doppler effect for sound waves, we have nu is equal to nu0 into 1 minus Vs by V, and nu' is equal to nu0 into 1 plus Vo by V. Let them be equations 1 and 2. Thus, in the case of sound waves, since the velocities of the source and the observer are relative to the medium in which they propagate, the effect on the frequency when the source moves away from the observer is different from when the observer moves away from the source. But this is not true in the case of Doppler effect for light waves. Let us now understand the reason for this. We know that the speed of an electromagnetic wave is same in any inertial frame of reference. As a consequence, for the purpose of Doppler effect of light, a source of light moving through a medium in which the observer is at rest and an observer moving through that medium with the source at rest are physically identical situations. Hence, we cannot use equations 1 and 2 in case of light waves. The expression for the Doppler effect of light is predicted based on the theory of relativity. The expression is nu is equal to nu naught into square root of c minus v by c plus v. Let this be equation 3. In this expression, c is the speed of light in vacuum and v is the velocity of the source with respect to the observer. V is taken along the line joining the source and the observer. V is positive when the source moves away from the observer and is negative when the source approaches the observer. Equation 3 can be mathematically manipulated as shown to obtain equation 4. If V is very much less than c, then v square by c square is much smaller than 1 in equation 4, and hence it can be neglected to obtain equation 5, where nu is equal to nu naught into 1 minus v by c. Equation 5 can be rewritten as nu minus nu naught whole divided by nu naught is equal to minus of v by c. If the change in the frequency nu minus nu naught is written as delta nu, then the fractional change in the frequency delta nu by nu naught is equal to minus v by c. Doppler effect of light has an important bearing in astronomy. When light emitted by stars is passed through a prism, a spectrum is obtained. In the visible part of this spectrum, lines of different wavelengths along with some intermediary dark lines are present. If a star moving away from us, there is an apparent increase in the wavelengths due to the Doppler effect of light, and hence the whole pattern of the spectrum gets shifted towards longer wavelengths. This is called the red shift. Our universe is continuously expanding. The astronomers have found an experimental proof for this in the red shift. When a star is moving towards the observer, there is an apparent decrease in the wavelengths and the whole pattern of the spectrum gets shifted towards shorter wavelengths. This is called the blue shift. It is important to note that we can measure either the red shift or the blue shift very accurately by comparing the apparent wavelengths of the spectral lines with the known laboratory wavelengths. When two waves reach a point in space at the same time, the resultant displacement of the particle is given by the principle of superposition. According to this principle, the resultant displacement, y, is the vector sum of the displacements y1 and y2 caused by two waves. For coherent sources, the waves generated by them will have the same amplitude, same frequency, and the phase difference between them is constant with respect to time. The waves from coherent sources can interfere constructively or destructively. If they interfere constructively at a point, the individual displacements are numerically added to give the resultant displacement at that point. When they interfere destructively at any point, the individual displacements cancel each other and the resultant displacement at that point is the minimum. You have already learned that for constructive interference, the path difference must be equal to n lambda, where lambda is the wavelength of light used and n is an integer. In terms of the phase difference, phi, the condition for the constructive interference is given by phi is equal to 0 or plus or minus 2 pi or plus or minus 4 pi and so on. For destructive interference, either the path difference is equal to n plus half into lambda or the phase difference phi is equal to plus or minus pi or plus or minus 3 pi and so on. If light has wave nature, it must exhibit the phenomenon of interference. When Huygens proposed the wave theory of light in 1678, there was no experimental proof for the interference of light. Subsequently, in 1801, Thomas Young demonstrated experimentally that light exhibits the phenomenon of interference. Let's study about Young's double-slit experiment. Take an opaque screen with a small pinhole S and place a monochromatic light source to the left of the screen. Now, the pinhole S acts as a point source of light and propagates spherical light waves to the right of the screen in all directions. Place another opaque screen with two very closely separated pinholes S1 and S2 to the right of the first screen. When S1 and S2 are illuminated by the incident light from S, they behave like 2 point sources of light and emit spherical waves to the right of the screen. In fact, S1 and S2 behave like virtual coherent sources of light. These spherical waves from S1 and S2 can be made to interfere on the screen GG' placed in their path. They form a series of bright and dark bands called interference fringes on the screen. The bright bands correspond to constructive interference of light and dark bands correspond to destructive interference of light. Let's now study the interference pattern in detail. Let the distance between S1 and S2 be d, and the distance between the pinholes and the screen be d. Let AB be the perpendicular bisector of the line joining S1 and S2, and O be the point of intersection of the line and the screen. We shall now consider an arbitrary point P on the screen along a line GG' perpendicular to AB and passing through O. Let the distance OP be x. Light from the two sources S1 and S2 covers a distance of S1P and S2P respectively to reach the point P. If P corresponds to an interference maxima, then the path difference S2P minus S1P is equal to n lambda. Let this be equation 1. On the other hand, if P corresponds to an interference minima, the path difference S2P minus S1P is P equal to n plus half into lambda. Let this be equation 2. Here, lambda is the wavelength of the light waves and n is an integer. From the diagram, as shown, we can write that S2p square is equal to d square plus x plus d by 2 whole square. This is equal to d square plus x square plus d square by 4 plus xd. Similarly, S1p square is equal to d square plus x minus d by 2 whole square. This is equal to d square plus x square plus d square by 4 minus xd. Therefore, S2p square minus S1p square is equal to 2xd. This equation can also be written as S2p minus S1p is equal to 2xd by S2p plus S1p. If capital D is much greater than the small d, then we can assume that S2p plus S1p is approximately equal to 2d. Then the path difference S2p minus S1p is equal to x into d by d. Let this be equation 3. From equations 1 and 3, the condition for point P to correspond to a bright band is x into d by d is equal to n lambda, or x is equal to n lambda d by d. Let this be equation 4. From equations 2 and 3, if x d by d is equal to n plus half into lambda, then at point P we will have a dark fringe. That is, for a dark fringe, x is equal to n plus half into lambda into d by d. Let this be equation 5. Here, n is equal to 0, or plus or minus 1, or plus or minus 2, and so on. The distance between the centers of consecutive bright fringes or consecutive dark fringes is called the fringe width. If xn and xn plus 1 are the distances of the nth and n plus 1th bright or dark fringes from the central bright fringe, then mathematically fringe width is equal to xn plus 1 minus xn. From equation 4, the fringe width for a bright fringe can be written as lambda d by d. From equation 5, the fringe width for a dark fringe can also be written as lambda d by d. Hence, the fringe width is the same for both the dark and bright fringes, which means the dark and bright fringes are equally spaced. If the fringe width is represented by beta, then beta is equal to lambda d by d. Let this be equation 6. If the central point O is considered to be equidistant from both the sources S1 and S2, then S1O is equal to S2O. This condition corresponds to n equal to 0 condition for a bright fringe, and hence we will have a bright spot at O. Now consider a line on the screen that passes through the point O and is perpendicular to both the lines AB and GG'. All the points on this line will be equidistant from S1 and S2, and hence we will have a bright central fringe along this line. On either side of this central bright fringe, we will have dark fringes. If n is taken as 0 in the equation 5, we get the value of x equal to lambda d by 2d. Likewise, we will have alternate dark and bright fringes on either side of the central bright fringe. Note that a particular fringe corresponds to the locus of points with a constant path difference of S2p minus S1p. Mathematically, Locus of such points represent a hyperbola. In fact, the fringe pattern is strictly a hyperbola. But for a large distance d, the fringes will be very nearly straight lines. Now look at equation 6 once again. The fringe width of an interference pattern is directly proportional to the wavelength of the interfering light waves. The fringe width is maximum for red light and minimum for violet light. The fringe width is inversely proportional to the distance d between the two sources S1 and S2. If we decrease the distance between the two sources, the fringe width increases. One more factor that influences the fringe pattern is the distance d between the sources and the screen. Fringe width is directly proportional to d. The actual separation between the fringes increases with the increase in distance of the screen from the two sources. Note that the angular separation of the fringes remains constant as the value of d changes. In the experiment discussed so far, the original point source S is assumed to be on the perpendicular bisector of the line joining S1 and S2, and the central bright fringe occurs at O. Let's now observe the changes that take place in the interference pattern when point source S is shifted to a different position S'. Let point Q be the midpoint of S1 and S2, and the angle SQS' be phi. The central bright fringe is now shifted from O to O'. The location of O' is such that all the 3 points S', Q, and O' lie on a straight line, and the angle SQS' is equal to angle OQO'. So far, we have observed the interference pattern formed by light waves emitted by 2 point sources. All the fringes are straight lines, even though the waves from the sources are spherical in shape. If we add some more pairs of point sources horizontally, each pair of point sources form the interference pattern at the same location. Hence, the intensity of the bright fringes increases. If the point sources are replaced with slits, a similar straight interference pattern is formed with increased intensity. What happens if we use 2 separate sources of light in place of S1 and S2? We don't observe any interference pattern on the screen. This is because the light waves coming out from 2 independent sources of light will not have any fixed phase relationship. Hence, they behave like incoherent light sources. We do not observe any interference pattern even when we use an ordinary monochromatic light source to illuminate both S1 and S2. The atoms in an ordinary light source radiate light in an unsynchronized and random phase relationship. Thomas Young had overcome this problem by using light waves from a single slit to illuminate S1 and S2. In this setup, any abrupt phase change in the source would reflect in exactly similar phase changes in the light coming from S1 and S2. Since laser light is coherent, we observe interference pattern when S1 and S2 are illuminated by laser light. Let us consider a home setup where the music is audible from the adjacent room. How can we hear sound when we cannot see the sound player? This is because the sound waves bend around the corners to reach our ears. This phenomenon of bending of waves around an obstacle in their path is known as diffraction. All types of waves exhibit this phenomenon. Observe the diffraction of water waves at a narrow slit placed on its path. When the size of the slit is large, the diffraction of water waves is quite negligible. On the other hand, when the size of the slit is very small, we observe the diffraction of water waves very clearly. The diffraction of waves depends on its wavelengths. If the size of the obstacle or the slit is of the order of the wavelength of incident waves, then diffraction occurs. This condition is also applicable to light waves. The wavelength of visible light is in the range of 400 to 800 nanometer. Since the wavelength of visible light is much smaller than the dimensions of most of the obstacles it encounters, we usually do not observe any diffraction. If a screen is placed behind an opaque object, light from the point source travels in a straight line and forms a shadow on the screen. But if we look at the shadow closely, we observe that no sharp boundary exists between the shadowed and the illuminated regions. The illuminated region above the shadow of the object contains alternate bright and dark fringes because of diffraction of light, and the pattern is called diffraction pattern. Let us now study diffraction of light at a narrow slit. Place a monochromatic light source on one side and a screen on the other side of a narrow slit. When the slit is illuminated by monochromatic light, a diffraction pattern is formed on the screen. The diffraction pattern consists of a central bright band, which may be much broader than the width of the slit, with alternate dark and bright bands on both sides. The intensity of the fringes decreases very rapidly. Let us now analyze the diffraction pattern mathematically. We represent light as a beam of rays. Let the width of the slit, Ln, be A. Let the source of monochromatic light and the screen be very far away from the slit. If the source is at a faraway distance, we can regard the incident light as plane wavefronts, or alternatively, the incident rays are parallel. When a plane wavefront is incident on the slit, all the points of the plane wavefront are in phase. According to Huygens' principle, every point on the wavefront acts as a source of secondary wavelets that spread out in all directions with a speed equal to the speed of propagation of the wave. Consequently, we find so many microscopic point sources of light between L and N, which produce secondary wavelets. The diffraction fringes formed on the screen are due to the interference of these secondary wavelets produced by a large number of point sources. Since the screen is at a faraway distance, we can regard the rays as parallel. The diffraction formed in such conditions is known as Fraunhofer diffraction. Consider an arbitrary point P on the screen. Let us examine the conditions for point P to be a diffraction maxima or a diffraction minima. Let M be the midpoint of the slit and a straight line passing through M be perpendicular to the plane of the slit, which meets the screen at C. Let the line joining the points M and P make an angle theta with the normal MC. Consider light rays from 2 point sources L and N separated by a distance A reach the point P. The path difference between these rays NP minus LP is equal to NQ. From triangle LNQ, NQ is equal to A sin theta. But for small angles of theta, sin theta is approximately equal to theta. Therefore, the path difference is equal to a theta. Now we shall analyze how contributions from a large number of sources produce diffraction fringes on the screen. Let us first consider the central point C. From the figure, we can see that angle theta is 0 for point C. That means waves from all the point sources reach C in phase, and hence all path differences are also 0. Which means waves from all parts of the slit contribute in phase at C. They interfere constructively and produce maximum intensity at C. Now consider another point C1 on the screen, such that a by 2 into theta is equal to plus or minus lambda by 2. Let this be equation 1. Imagine that the slit is divided into two equal halves, LM and MN, with a width of a by 2 each. Consider the waves from the point sources located at L and M reaching the point C1. Since these two sources are separated by a by 2, the path difference between them at the point C1 is equal to a by 2 theta. Let this be equation 2. From equations 1 and 2, we can conclude that the path difference between L and M at C1 is 1/2 of the wavelength of the incident light. Hence, the waves from L and M are out of phase and interfere destructively at C1. Now, if both the half slits LM and MN are considered for every wave passing through LM, there is a corresponding wave passing through MN originating at a point a by 2 below the first one, such that the two waves are out of phase at C1. Hence, every wave arriving at C1 from the upper half of the slit LM interferes destructively with the one coming from the bottom half of the slit MN. The intensity at C1 is therefore 0, and C1 corresponds to the first minimum of the diffraction pattern. Hence, the condition for the first minima is theta is equal to plus or minus lambda by A. Let this be equation 3. Equation 3 implies that the central maxima can be made wider by making the slit narrower. We can also divide the screen into 4 parts, 6 parts, and so on. And using a similar argument, we can show that the subsequent diffraction minima occur whenever theta is equal to plus or minus 2 lambda by A, plus or minus 3 lambda by A, and so on. So, the general condition for a diffraction minima can be written as theta is equal to n lambda by A, where n is an integer. Let this be equation 4. In between two successive minima, we will have secondary maxima. We can find the location of the secondary maxima for values of theta approximately equal to n plus half into lambda by A. Let this be equation 5. Let us now verify the validity of equation 5. Imagine that the screen is split into 3 equal parts of width a by 3. Consider a point C0 approximately between C1 and C2 at an angle theta equal to 3 lambda by 2a. Now consider 2 waves from the ends of the 2 top parts. Since the width of each part of the slit is a by 3, the path difference between them at C0 is equal to a by 3 into theta, which in turn is equal to lambda by 2. Hence, these 2 waves interfere destructively at C0. In the same way, all the waves from the first part can interfere destructively with corresponding waves from the second part of the slit. Only the remaining 1/3 of the slit contributes to the intensity at C0. Therefore, the intensity of the secondary maxima is much weaker than the intensities of the central maxima. The intensity distribution due to diffraction of light is as shown. So far, we assumed that the source and the screen are placed far away from the slit. In such cases, the intensity of the fringes on the screen is less. If a converging lens is placed after the slit and the screen is placed at the focal point of the lens, then the parallel rays from the slit converge onto the screen to give a bright diffraction pattern. Note that the lens do not create any extra path difference in a parallel beam of light. A wave traveling through a distance delta x in a medium of refractive index n suffers the same phase change as when it travels a distance n delta x in vacuum. This means that the path difference delta x in a medium of refractive index n is equal to a path difference of n delta x in vacuum. The quantity n delta x is known as the optical path of the light. Since the optical path of rays converging at any point on the screen is the same for all the rays, the lens do not create any extra path difference in a parallel beam. Let us now compare the diffraction fringes due to a single slit with the interference fringes formed in the double slit experiment. We observe alternate bright and dark fringes in both the interference and the diffraction experiments. The fringes in case of the interference experiment are due to superposition of waves from two sources, whereas the diffraction pattern is a superposition of waves originating from each of the point sources on the single slit. The interference pattern has a number of equally spaced bright and dark bands, but the diffraction pattern has a wider central bright maximum. The intensity of the successive maxima decreases as we move away from the central maxima on either side. In the case of diffraction, the first minima is formed at an angle theta equal to plus or minus lambda by a, whereas the condition of angular separation theta equal to plus or minus lambda by a corresponds to the central maxima for two-slit interference pattern with a equal to the separation between the slits. Now, observe the intensities of the fringes formed in the single-slit diffraction and the double-slit interference experiments. When observed closely, double-slit interference experiments, we see a decrease in the intensity of the bright fringes as we move towards either side of the central maxima. This happens because of the diffraction of light from each of the single slits. In fact, the pattern is a superposition of a double-slit interference pattern and a single-slit diffraction from each slit. The combined effects of diffraction and interference are as shown. The diffraction pattern acts as an envelope and controls the regularly spaced interference pattern. The number of interference fringes occurring in the broad diffraction peak depends on the ratio d by a, where d is the slit separation and a is the width of each slit. As the value of a decreases, the diffraction pattern becomes flat and we observe a normal interference pattern. Imagine that while looking down the road at night, you observe a distant light that becomes brighter and brighter, and then it splits into two light sources. When it comes closer, you recognize it as the headlights of a car approaching you. You weren't able to recognize it when the car was far away from you, because of the limitation of the human eye, and also of the optical instruments like telescope, etc. Distinguishing two distinct objects that are very close to each other with a very small angular separation between them is called resolving two objects. The minimum separation of two objects or points that can just be resolved by an optical instrument is called the limit of resolution of the instrument. The smaller the limit of resolution, the greater is the resolution or the resolving power of the instrument. The resolving power of an eye or of any other optical instrument is limited by diffraction of light. To understand this, let us first study diffraction of light by a circular aperture. Consider an opaque board with a small circular aperture. Allow a plane wavefront to be incident on it from one side and place a screen on the other side. The parallel beam of light is diffracted by the circular aperture, and we observe a diffraction pattern on the screen which consists of a central bright spot surrounded by alternate dark and bright rings. The central bright spot is called the airy disk. The intensities of the subsequent bright rings drop out very quickly as we move away from the central disk. In fact, 85% of light energy falls within the airy disk. Let us now describe the diffraction pattern mathematically. Let the diameter of the aperture be A. The distance between the aperture and the screen be D. And the wavelength of the incident light be lambda. If theta represents the angular radius of each ring, a complicated mathematical analysis of diffraction by a circular aperture shows that the first dark circle occurs at an angle theta given by the condition sin theta is equal to 1.22 lambda by A. Let this be equation 1. For smaller angles of theta, we know that both sin theta and tan theta are approximately equal to theta. Since the screen is at a distance d from the aperture, where d is much greater than A, which is the radius of the first dark ring, r is equal to d tan theta. Using equation 1, we can rewrite this equation as r is equal to 1.22 into lambda d by A. Let this be equation 2. The diffraction of light by a circular aperture is of great practical importance. In various optical instruments, such as telescopes, lenses are used. During image formation, a lens allows only a light that is incident on its circular aperture. Thus, a lens behaves like a circular aperture in an opaque screen. Let's consider a lens of focal length f with a screen at the focal plane of the lens. If plane wavefronts of light from a distant point object are incident on the converging lens, then the image formed is a diffraction pattern consisting of a central bright disk encircling bright and dark rings. This contradicts the assumption we made in ray optics. In ray optics, we assumed that a converging lens focuses light from a distant point object to form a point image on its focal plane. But if diffraction effects are taken into consideration, the image is in the form of a circular disk instead of a point. If the diameter of the lens is A, then, using equation 2, the radius of the first dark ring, r is equal to 1.22 into lambda f by A, where f is the focal length of the converging lens. Let this be equation 3. As we know that a lens forms a disk image of a point source, it limits the resolving two neighboring points imaged by a lens. Let S1 and S2 be 2 point sources of light placed before a converging lens. Due to diffraction, the images formed by the lens on the screen placed at the focal plane are two circular disks. If the two sources are closely placed, the disk images overlap each other and appear like a single disk. These two images are said to be unresolved. If the two sources S1 and S2 are moved apart, the centers of their image disks also move apart. For sufficient separation, one can distinguish the presence of two disks in the pattern. In this case, we say that the 2 point sources are resolved. Two images are said to be just resolved if the first minimum of one pattern coincides with the center of the other. This is known as Rayleigh criterion. This means that the radius of each bright disk should be equal to the separation between them. But as per equation 3, the radius of the central bright disk is equal to 1.22 lambda f by a. Hence, increasing the diameter A of the lens decreases the R value and as a consequence increases the resolving power of a lens. The concept of a converging lens focusing light from an object at an infinite distance to form an image at the focal plane is applicable to a telescope. The image so formed is not a point image, but a diffraction pattern with a bright central disk of radius r given by equation 3. So, in order to improve the resolving power of a telescope, the objective of the telescope must be large enough. In the case of a microscope, we place the viewing object very close to the objective lens. If f is the focal length of the objective lens, then the object is placed slightly beyond f. If a real image is formed at a distance of v, then the magnification m is approximately equal to v by f. Let this be equation 4. If d is the diameter of the objective lens, and 2 beta is the angle subtended by the objective lens at the focus of the microscope, then, from the figure, tan beta is approximately equal to d by 2 by f. Therefore, d by f is approximately equal to 2 tan beta. Let this be equation 5. If the first dark ring of the diffracted pattern is formed at an angle theta, then, from equation 1, we have sin theta is equal to 1.22 into lambda by d. For smaller angles of theta, theta is equal to 1.22 into lambda by d. Let this be equation 6. Since the image is formed at a distance of v from the lens, the radius of the central bright disk r is equal to v theta. Substituting the value of theta from equation 6, we get r is equal to v into 1.22 lambda by d. Let this be equation 7. If we have two objects separated by a small distance d before the objective of the microscope, we observe two diffraction patterns corresponding to the two images. As the separation between the two objects decreases, the distance between the two images also decreases. If the separation between the two images is less than r, then the images are not resolved. Let dm be the minimum distance between the objects and r be the separation between them. If m is the magnification, then we can write r is equal to m into dm, or dm is equal to r by m. On substituting the value of r from equation 7, we get dm is equal to v into 1.22 lambda by d whole divided by m. Since magnification m is equal to v by f, f is equal to v by m. Therefore, dm is equal to 1.22 into f lambda by d. Let this be equation 8. From equations 5 and 8, we get dm is equal to 1.22 lambda by 2 tan beta. For smaller angles of beta, tan beta is equal to sin beta approximately. Therefore, dm is equal to 1.22 lambda by 2 sin beta. Let this be equation 9. If the medium between the objects and the lens has a refractive index of n, then the expression for the minimum separation between the two objects dm is equal to 1.22 lambda by 2n sin beta. Let this be equation 10. The quantity n sin beta is called the numerical aperture of the objective of a microscope. The resolving power of a microscope is defined as the reciprocal of the minimum separation between the two objects seen distinctly. Let us now compare the functioning of the two optical instruments, the telescope and the microscope. A telescope produces images of distant objects nearer to our eye. Therefore, the objects which are not resolved at a faraway distance can be resolved by looking at them through a telescope. On the other hand, a microscope magnifies objects and produces their larger images. Hence, we can say that the telescope resolves, whereas the microscope magnifies. Let us now find the limits for the validity of ray optics. An aperture of size A, illuminated by a parallel beam, diffracts light into an angle equal to lambda by A approximately. This is the angular size of the bright central maximum. If Z is the distance of the screen from the slit, in traveling a distance Z, the diffracted beam acquires a width W, that is approximately equal to Z lambda by A. The value of Z, for which the spreading of the image due to diffraction is approximately equal to the size of the aperture A, is called Fresnel distance. That means, if W is equal to A, then Z is equal to ZF. Hence, ZF is approximately equal to A square by lambda. Hence, for distances smaller than the Fresnel distance, the spreading due to diffraction is also small. But for distances greater than ZF, the spreading due to diffraction is considerably large, and it dominates the assumptions of ray optics. Waves are classified into either transverse or longitudinal waves depending on the relationship between the direction of displacement of the oscillating element and the direction of propagation. If the displacement is along the direction of propagation of the wave, then the wave is called a longitudinal wave. Whereas, in the case of a transverse wave, the displacement is perpendicular to the direction of propagation of the wave. Polarization is a characteristic of all transverse waves. For example, waves on a stretched string are transverse in nature. An element of the string oscillates about its equilibrium position, perpendicular to the direction of wave propagation. Let us assume that the string is along the x-axis and its free end is moved up and down along the y-axis. The waves generated propagate along the x-axis and the displacement of any given element of the string is along the y-axis. Such a wave is mathematically described by y of xt is equal to a sine kx minus omega t, where a is the amplitude of the wave, omega is the angular frequency, and k is the angular wave number. The wavelength of the wave is lambda and is equal to 2 pi by k. If a wave has only y displacements and each point on the string moves in a straight line along the y-axis, then the wave is said to be linearly polarized in the y direction. The propagation of the wave and the displacement of any element of the string always lies in the xy plane, and hence it is also called a plane polarized wave and is referred to as xy polarized wave. Instead of moving the free end of the string up and down along the y-axis, if we vibrate it along the z-axis, then the displacement of any given element of the string is along the z-axis. The wave so generated is a z-polarized wave and is mathematically represented by z of x t is equal to a sine kx minus omega t. If the vibrations of the string are not confined to a given plane, then the wave is an unpolarized wave. Now let us study about light waves. Light waves, which are electromagnetic waves, are transverse waves, with the electric and the magnetic fields oscillating perpendicular to each other and to the direction of propagation. In the case of light waves, the direction of the electric field E is the direction of the polarization of the wave. For example, if E is always along the y-axis, then the light wave is a y-polarized wave. The plane determined by the E vector and the direction of propagation of the wave is called the plane of polarization of the wave. If E field remains in a fixed direction, then the wave is said to be linearly polarized or plane polarized. The electromagnetic waves used for radio and TV transmission are plane polarized. The light from sources like the sun or an incandescent light bulb do not show single plane polarization. Let us represent light using the E vector and its propagation as shown. The light from these sources is composed of many directions of the E vector distributed randomly around the direction of propagation of light. This light is transverse but unpolarized. An unpolarized light can be converted into a plane polarized light using Polaroids. A Polaroid consists of a long chain of molecules aligned in a particular direction. The components of the electric vector of the incident light, which are in the direction of the aligned molecules, get absorbed. The direction perpendicular to the direction of aligned molecules is known as the path axis. That means the path axis of a Polaroid is the polarizing direction. If an unpolarized light wave is incident on a Polaroid, the Polaroid sheet transmits only that light which has its electric field vector vibrating parallel to path axis and absorbs the light with E vector vibrating at right angles to path axis. Now, consider a Polaroid sheet placed in the path of a plane polarized light. The vector E shows the plane of vibration of the light incident on the Polaroid sheet. If EY and EZ are the components of E, such that EY is parallel to the path axis and EZ is at right angles to it, then only the EY component passes through the Polaroid sheet. Now allow light from an ordinary source to pass through the Polaroid P1 and incident on a screen. It is experimentally observed that the intensity of the polarized light transmitted through the sheet is half the intensity of the incident light. Rotating P1 has no effect on the transmitted beam and transmitted intensity remains constant. This can be explained as follows. In an unpolarized light, the direction of the E vector is randomly distributed around the propagation of light. We can resolve these different vectors into components EY along the polarizing axis and EZ perpendicular to the polarizing axis. If the intensity of the incident light is 2I0, then, because of symmetry, the intensity of light in the direction of the polarizing axis is I0 and the intensity of light in the perpendicular direction is I0. The Polaroid allows only the EY component of the incident light to pass through it, and hence the intensity of the transmitted light is half the intensity of the incident light. Let the intensity of the plane polarized light transmitted by the Polaroid P1 be I0. Now, place another Polaroid P2 between the first Polaroid and the screen in the path of the plane polarized light of intensity I0. The intensity of the light falling on the screen depends on the orientation of the Polaroid P2. If we start rotating the Polaroid P2, the intensity of light incident on the screen reduces to nearly zero at one position and reaches its maximum when turned by 90 degrees from the position of zero intensity. This can be understood by considering the orientations of the path axes of the two Polaroids. The light passing through the Polaroid P1 gets polarized along its path axis. If the path axis of the Polaroid P2 is perpendicular to the path axis of the Polaroid P1, then no light is transmitted through the Polaroid P2. If the path axis of the Polaroid P2 is parallel to the path axis of the Polaroid P1, then the entire light transmitted by the Polaroid P1 is also transmitted by the Polaroid 2, and hence the intensity is maximum. If the path axis of E1 makes an angle theta with the path axis of P2, then the component of E parallel to the path axis of the Polaroid P2 is equal to E cos theta. If Em is the amplitude of the light incident on the Polaroid P2, then its intensity I0 is equal to Em squared. The amplitude of the light emerging from the Polaroid P2 is then equal to Em cos theta, and the intensity of light I emerging from P2 is equal to Em square cos square theta. This can also be written as I is equal to I naught cos square theta. This is known as Maloo's law. Polaroids are used in sunglasses, window panes, and also in cameras as filters to control the intensity of light. Let us first study about polarization by scattering. When light waves propagate in a medium, they cause the electrons of the atoms of the medium to oscillate periodically. In fact, these oscillations of the electrons are in the direction of the electric field vector of the incident light. We know that these oscillating electrons emit radiations. The propagating wave is a result of the incident light and the radiations from the oscillating electrons. Consider the propagation of light in a transparent solid. In such a case, it is experimentally observed that the oscillating electrons radiate in the direction of propagation of light, and hence, the resultant wave has maximum intensity in the direction of the incident light. Therefore, in case of solids, the percentage of light scattered in the sideway direction is very less. In a liquid or in a gas, the sideway scattering is more when light propagates through them. The molecules of a liquid or a gas are usually separated by large distances and are bound together loosely. The oscillating electrons of these molecules act independently and scatter more light sideways. Let us now consider the propagation of light through a gas. Assume that the propagation of light is along the x-axis. If the light is polarized in the xy plane, then it makes the electrons of the gas molecules oscillate along the y-axis. But, in case of transverse electromagnetic waves, an oscillating electron does not radiate along the direction in which it oscillates. Hence, the scattered light is in the xz plane. If the incident light is Z polarized, then the scattered light is in the yx plane. Now, if an unpolarized light, like the sunlight, propagates through the atmospheric air in the direction of the x-axis, different electrons of the air molecules oscillate in different directions and scatter light in different directions. If we look at the light scattered sideways by gas molecules, we can find that it is wholly or partially polarized. If we consider an observer situated such that he is along the direction perpendicular to that of the propagation of light, he observes the light to be completely polarized. If the observer is situated along the direction of the z-axis, then the scattered light received by him is y-polarized. Unpolarized light can also be totally or partially polarized by reflection. Consider an unpolarized light incident on an interface between two transparent media. We know that it will be partially reflected into the first medium and partially reflected into the second medium. We know that the plane of incidence is defined as the plane containing the incident light, reflected light, and the normal to the surface at the point of incidence. It is experimentally observed that waves for which the E vector is perpendicular to the plane of incidence are reflected more strongly than those for which the E vector lies in the plane of incidence. Note that the E vector, perpendicular to the plane of incidence, is parallel to the reflecting surface. That means the reflected light is partially polarized in the direction perpendicular to the plane of incidence. But for a particular angle of incidence, known as the polarizing angle or the Brewster's angle, the light for which E lies in the plane of incidence is not reflected at all, but is completely refracted. When light is incident at the polarizing angle, the light for which the E vector is perpendicular to the plane of incidence is partially reflected and partially refracted. The light for which the E vector lies in the plane of incidence is completely refracted into the second medium. This means, at the angle of incidence of the polarizing angle, the reflected light is completely polarized perpendicular to the plane of incidence, and the refracted light is partially polarized. The intensity of the refracted light is much more than the intensity of the reflected light. At the polarizing angle, it is experimentally found that the reflected and the refracted light are at right angles. If the polarizing angle is IB, then the angle of reflection is also equal to IB. Let R be the angle of refraction. From the figure IB, plus 90 degrees plus R is equal to 180 degrees. Simplifying, we get IB plus R is equal to 90 degrees. Let N1 be the refractive index of the first medium and N2 be the refractive index of the second medium. From Snell's law, N1 sin IB is equal to N2 sin R. On combining these equations, we get N1 sin IB is equal to N2 sin 90 minus IB. This can be written as N2 by N1 is equal to sin IB by cos IB. This means the refractive index of the second medium with respect to the first medium, N21, is equal to tan IB. This is known as the Brewster's law. Now use a good polarizer and completely remove all the light with its E vector perpendicular to the plane of incidence, and allow it to fall on the interface at the Brewster's angle. The light incident is completely transmitted and no light is reflected back into the medium 1. This means we can have total transmission of light. Interference is a phenomenon exhibited by all types of waves. When identical waves from two sources overlap at a point in space, the resultant wave intensity at that point can be greater or less than the intensity of either of the two waves. This phenomenon is called interference. Here, identical waves mean that the interfering waves have the same frequency and amplitude, and the phase difference between them is constant with time. When the resultant intensity is greater than the individual intensities, the interference is said to be constructive. If the resultant intensity is less than the individual intensity, then the interference is destructive. The phenomenon of interference can be explained on the basis of the superposition principle of waves. According to the superposition principle of waves, at a particular point in the medium, the resultant displacement produced by a number of waves is the vector sum of the displacements produced by each of the waves. Let us understand the superposition principle and the interference of waves by considering the waves on the surface of still water. Two needles are placed above the water surface and made to oscillate up and down periodically. The 2 points S1 and S2, where the needles dip in the water, act as the two sources of waves. Let P be a point on the surface of the water. When waves generated at S1 reach the point P, the point executes simple harmonic motion. Let y1t be the displacement of the particle P due to waves from S1. Similarly, when waves generated at S2 reach the point P, the displacement caused is given by y2t. If waves from both S1 and S2 reach the point P simultaneously, the resultant displacement yt is given by the superposition principle as yt is equal to y1t plus y2t. If waves produced by two sources have the same frequency and the phase difference between them does not change with time, then such waves are said to be coherent, and the two sources are called coherent sources. Let us assume that the two sources S1 and S2 are coherent and generate waves of amplitude A and angular frequency omega. Consider a point P on the perpendicular bisector of the line joining the two sources S1 and S2. For such points, S1P is equal to S2P. Since both the sources are at the same distance from P, the waves reaching the point P are also in phase. If the displacement produced at P due to the waves generated at the source S1 is given by the equation y1 is equal to a cos omega t, then the displacement at P due to the waves from S2 can also be represented by y2 is equal to a cos omega t. We know that the intensity of a wave is proportional to the square of its amplitude. Therefore, if I0 is the intensity produced by each of the sources, then I0 is proportional to a square. The resultant displacement at P, y is equal to y1 plus y2. On substituting the values of y1 and y2, we get y is equal to 2a cos omega t. If I is the resultant intensity at P, then I is proportional to 4a square. In terms of intensity of individual waves, I is equal to 4I0. The resultant intensity is 4 times the individual intensities. Hence, we say that the two waves interfere constructively. Now consider a point Q such that S2Q minus S1Q is equal to 2 lambda, where lambda is the wavelength of the waves. Here, 2 lambda is the difference in the distance travelled by the waves to reach the point Q and is known as the path difference. The waves from S2 will reach the point Q 2 cycles after the arrival of the waves from S1. Hence, the path difference of 2 lambda is equal to a phase difference of 4 pi, and the phase difference between the waves arriving at the point Q is equal to 4 pi. If the displacement produced at the point Q due to the waves from S1 is given by y1 is equal to a cos omega t, then the displacement produced by waves from S2 is represented by y2 is equal to a cos omega t minus 4 pi. But this is again equal to a cos omega t. The resultant displacement of Q, y is equal to y1 plus y2. On substituting the values of y1 and y2, we get y is equal to 2a cos omega t. And the intensity will be again equal to 4I0. Now, let us consider another point R such that S2R minus S1R is equal to minus 2.5 lambda. Since the path difference between the two waves reaching the point R is 2.5 lambda, the corresponding phase difference would be 5 pi. This means that the waves from S1 will arrive exactly 2.5 cycles later than the waves from S2. Thus, if the displacement produced at the point R due to the waves from the source S1 is given by y1 is equal to a cos omega t, then the displacement due to the waves from S2 will be y2 is equal to a cos omega t plus 5 pi, which is equal to minus a cos omega t. The two displacements y1 and y2 are out of phase. If the net displacement at R is y, then y is equal to y1 plus y2, which is equal to 0. Hence, the intensity at R is 0. The two waves are said to interfere destructively, and this is known as destructive interference. Hence, if waves are emitted by two coherent sources like S1 and S2, the general condition for constructive interference of these waves at a point P is the path difference between S1P and S2P must be equal to n lambda, where n is a positive integer. Let this be equation 1. At the point of constructive interference, the resultant intensity is 4 times the individual intensities. If the point P is such that the path difference between S1P and S2P is equal to n plus half into lambda, where n is a positive integer, then we will have destructive interference. Let this be equation 2. For destructive interference, the resultant intensity is equal to 0. Since the two sources are coherent, the resultant intensity at any point does not change with time. If the two sources emit waves continuously, constructive interference takes place at some points and destructive interference at other points. That means, points for which equation 1 is satisfied, constructive interference takes place, and the intensity at those points is 4 times the individual intensities. For other points where equation 2 is satisfied, we have destructive interference and the intensity is 0. The curves shown in the image form the locus of all points for which the path difference is an integral times the wavelength. They denote all points on which constructive interference occurs. In between these curves, we have curves indicating the locus of all those points for which the path difference satisfies equation 2. Note that, in case of interference, the energy is redistributed. Consider an arbitrary point E such that the path difference between S1E and S2E does not satisfy the condition for either constructive interference or destructive interference. Let the phase difference between the displacements caused by the two waves at the point E be phi. At the point E, if the displacement caused by the waves produced at the source S1 is represented by y1 is equal to a cos omega t, then the displacement caused by the waves from S2 will be y2 is equal to a cos omega t plus phi. The resultant displacement at E will be y is equal to y1 plus y2. Substitute the values of y1 and y2 in the above equation. And on further simplification, we get y is equal to 2a cos phi by 2 into cos omega t plus phi by 2. The amplitude of the resultant displacement is equal to 2a cos phi by 2. Therefore, the intensity at E is I equal to 4a square cos square phi by 2. This can also be written as 4I naught cos square phi by 2. Let this be equation 3. Equation 3 is a general expression which enables us to find the intensity at any point on the surface. If the phase difference phi is equal to 0, or plus or minus 2 pi, or plus or minus 4 pi, and so on, then cos phi by 2 is 1, and hence I is equal to 4I naught. These points represent the interference maxima. This is the general condition for constructive interference in terms of phase difference. If the phase difference phi is equal to plus or minus pi, or plus or minus 3 pi, and so on, we will have destructive interference leading to zero intensity. These points are the interference minima. This represents the general condition for destructive interference in terms of phase difference. If the two sources are coherent, then the phase difference at any point does not change with time. Hence, the interference pattern formed is stable. If the phase difference phi is not constant and changes with time, then the interference pattern formed will also change with time. The positions of maxima and minima will also change with time. If these changes happen very rapidly, we observe a time-averaged intensity distribution. Mathematically, the average intensity is equal to 4I naught into the average of cos square phi by 2. But we know that if phi of t varies randomly with time, the time-averaged value of cos square phi by 2 is equal to 1 by 2. In such cases, the resultant intensity is given by I is equal to 2I naught. That means the two intensities are just added up. So we need coherent sources to produce a stable interference pattern.
दोस्तों, यदि आज की वीडियो आपको अच्छी लगी हो तो लाइक कीजिए, चैनल को सब्सक्राइब कीजिए और अपने दोस्तों के पास इस वीडियो को शेयर कीजिए। अगर आपका कोई कमेंट हो तो कमेंट बॉक्स में नीचे ज़रूर लिखें। थैंक यू।